Hello everybody, welcome back to our channel. In today's episode, we're going to be solving a Physics 7B torque practice problem, the windy day at the playground. As usual, if you're finding this content helpful, please leave a like and subscribe. Okay, so let's go ahead and read the problem. Feel free to pause if you need to in order to copy the problem. So we have a 3 kilogram platform and it is held by 2 ropes as shown below. The wind is blowing to the left, adding a 10 newtons horizontal force applied on the right side. While the wind is blowing, the platform is perfectly still. Assume that the center of mass is in the center of the platform. The questions are, we need to show that the vertical components of the tension on the left and the right must be equal, and then giving a certain angle, we need to find an actual number for the right tension. So as you can see, I've written everything over here in my notes. So I have basically the same drawing that the problem gave us, and I just added the mass of the beam, 3 kilograms, and then force by air, I just added the actual number, 10 newtons. And I also went ahead and started by drawing an extended force diagram of this problem. This problem I decided to mark as red. So I'm going to be assuming that by the time that you get to the red problems, you have already seen the green ones and the yellow ones. So you are very much used to seeing extended force diagrams, but I'll explain it. So this force we have because the mass has a weight. So because the mass has, this beam has a mass, that means that it has a weight, which is force by gravity. Force by gravity is mg. So if this is 3 kilograms, then I just use g is equal to 10 to come up with this 30 newtons. Force by air is exactly the same, so it's just 10 newtons. And because this swing is hanging from 2 strings, then we have 2 tension forces, which I decided to label according to the problem. So I decided to go with TL and T right. This angle was not explicitly labeled in the problem, but because we have the angle on the left, I decided that I would call this the angle on the right. Now, the thing that we basically have to prove per the instructions of the problem is that the vertical component of this tension, which would be this component, which I'm going to call left Y component, has the exact same magnitude as this component, which I'm going to call right Y component. Now, under normal circumstances, which is under not a windy day, these 2 vectors would be exactly the same because the swing would just be balanced at the center and everything would sort of be symmetric. However, this force by air brings some breaks up the symmetry, which means that this angle is not equal to this angle, and that means that this magnitude is not equal to this magnitude. However, the problem is asking us, well, can you prove that even if these 2 are different in magnitude, that their Y components are still going to be the same? So let's just go ahead and try that out. The first thing that I'm going to do is figure out a way to write what the problem wants in terms of an equation. Because if I have an equation that I can see, then it's just easier for me to get there. So just by using SOHCAHTOA, what they want me to prove is that if I multiply TL times cosine, so just go ahead and look at this triangle and just see that this component right here is touching the angle. So what we want is to show that TL magnitude times cosine of this angle is equal to T right magnitude times cosine. Again, this angle is actually touching this of this angle. So this is what we want. We haven't shown anything. We have just, this is what we want. We want ideally an equation that shows this. So what are we gonna do? Well, this is the most difficult part of the problem because essentially we can do whatever we want, and that's a little bit scary. Now, this is a torque problem, so obviously the solution is gonna somehow have, just have something to do with torques. But we don't even have a pivot point to work with, and that is sometimes the most daunting things for students, because this is one of those problems in which you have to choose what pivot point you're going to use. Now, this thing is not rotating around any pivot point, which means that you could literally pick your pivot point at whatever, place you want, and that is going to be a valid option physics-wise. So you could just randomly decide, hey, this is going to be the pivot point, and that would be okay. Or this is going to be the pivot point, and that would be okay. However, of course, some pivot points are more advantageous than some other pivot points, and so some pivot points are far more obvious than some other pivot points. So the way in which I like to, quote unquote, figure out what pivot points I'm going to use is that I kind of take a step back and just look into the physical situation and try to come up with what I, myself decided to call the natural pivot points of this problem. And what do I mean by that? Well, let me just show you. To me, one of the very natural pivot points of this problem would be this side of the beam, which is this side of the beam. And why am I calling this point a natural pivot point? Well, that would be because if I break this string, then this beam is going to start rotating around this pivot point. So even though nothing is spinning around this pivot point, I do like to think about it as one of the natural pivot points of this problem. Now, what would be the other quote-unquote natural pivot points of this problem? Well, that would be this part right here. Because again, if you just look at the physical situation that you were given, if you break this string, then all of this beam is basically going to start rotating around this pivot point. So those are the two pivot points that, at least to me, seem the most natural. Again, they are not the only two valid pivot points, and I believe that the solution uses the center of the rod as a pivot point, which I don't disagree with. There's nothing physically wrong with that, but personally, that is just not how I would solve this problem, and I am solving this problem as I would solve this problem. So I'm just gonna go ahead and use my two pivot points, my two natural pivot points, in order to figure things out. So I'm gonna start with the green pivot point, which means that I'm gonna balance my torques around this star over here. My torques need to balance out to 0, because even though this is a natural pivot point, nothing is really spinning. And if I use this star as my pivot point, out of these 4 forces, 1, 2, 3, 4, how many of these forces are generating a torque? Well, only these 2 forces are generating a torque. Why is that? Well, TL is not generating a torque because R is equal to 0. And this force by air is not generating a torque because it's parallel to the pivot point. Which means that with the green star as a pivot point, the only 2 pivots that I have are torque by gravity and torque by the right string. Now, torque by gravity, let's just go ahead and use our, our basic torque is equal RF sine of angle equation. Torque by gravity is equal to L halves, because it's half the length, times 30, times sine of 90 degrees, which is equal to 1, so I'm not going to write that. Now the torque on the right is equal to R is equal to L, because it's the entire length of the beam, times TR, times sine, but we need to be careful. This is not sine of just this angle. This is the sine of this angle plus this part right here. So this would be the sine of the angle right plus 90 degrees. And this has to be equal to 0. Now I'm going to go ahead and solve for this chunk right here. So the L's are going to cancel out. And my equation that I get from balancing my torques around the green star is dr sine this angle plus 90 is equal, oh, and this is negative because this torque is actually going into the page. So sorry about that, but yeah, so this has to be negative because if you use your right hand rule, torque by gravity goes into the page while torque by the right string goes out of the page. Into the page is negative, so I was missing this. So this goes to the other side of the equation, and this is equal to 15 because that's 30 divided by 2. So I'm just gonna go ahead and keep this. Now I'm gonna repeat my exercise. But now I'm gonna balance my torques around the blue star. So if I balance my torques around the blue star, how many of these four torques generate, how many of these four forces, generate a torque? Well, dr is not generating a torque because it's being applied at the pivot point. Force by air is not generating a torque because it's parallel to the pivot point. So the only two torques that are the only two forces that are generating a torque are force by gravity and this tension force. So let's just balance that out. So this would be left, and they have to be equal to 0. Now, using the right hand rule, this torque is going out of the page, and this torque is going into the page. So let's just go ahead and write that in terms of, RF sine of the angle. Torque by gravity is going to be plus L halves times 30. Torque by this left string is going to be L TL sine of not just this angle. Remember, it has to be the angle between the r vector and this vector, so it has to be this whole angle, which would be this angle, plus 90 degrees is equal to 0. And if I solve in a similar manner that I solved for this one, meaning if I solve for just this part right here, L's cancel out, that is TL sine of this angle plus 90 degrees is equal to positive 15. So those are the two equations that come from balancing our torques. And as you can see, this is already starting to look like the thing that we are looking for. Because if these two things are equal to 15, well, if you just rewrite that, then if both of them are equal to 15, what you're saying is that dr sine of angle r plus 90 is equal to TL sine of this angle plus 90, right? So this is almost exactly what we want. The only difference is that what we originally wanted was this cosine, which comes from doing basic SOHCAHTOA over here, and what we have is just this weird sine. First of all, it's a sine, and then it's a sine of this angle plus 90. So this is a little awkward. However, even though it might seem like we didn't get anywhere, or like maybe we did a mistake, we actually did not, because if you remember your trigonometric properties, and this is just a general property, it works every time. Cosine of an angle is equal to sine of that angle plus 90 degrees. This is not only relevant for this problem. This is, this rule 100% applies. If you use it on your calculator for like 15 degrees, you'll see that for whatever angle you want, let's just work with 15, cosine of 15 is equal to 0.96. Well, sine of 15 plus 90, guess what? Same number, because this is a property. It always holds. So by proving this, essentially, we just proved that TL cosine of this angle is equal to TR cosine of this angle. So this basically completes the proving part. This arrow has to be exactly equal to this arrow, and this is the proof. Now again, I use 2 pivot points. I require the use of 2 pivot points to arrive to this result. Maybe there is a more clever way. I don't negate that. The only thing is this is basically how I would solve it, and this is how the problem looks easy to me, even though I needed to do this procedure twice. I am the sort of person that would rather do an easy procedure twice than do a harder procedure that I might get stuck in once. So this is just my style of solving a problem. But anyway, the second part of this problem is asking us, well, now that you have this relationship, if the left angle is exactly 25 degrees, then what is the vector t on the right? Now, the first thing that we have to do in order to solve this problem is to use this information in order to completely figure out both the x and the y components of TL. So let's just go ahead and do that. The y component of TL we already know because of this equation. We already said that this is equal to cosine, so the y component is going to be equal to 15. So let's just write that. TL in terms of x and y component, the y component is equal to 15. Now the x component is just basically the magnitude of TL times sine of the angle. So let's just go ahead and find the magnitude of TL. In order to find the magnitude of TL, we can just use this equation right here. And basically what we have to do is substitute 25 degrees here, send this part dividing, and that is how we're gonna find TL. So let's just go ahead and do that. So TL is equal to 15 divided by sine of 25 degrees plus 90 degrees. And that is equal to 16.55. So this total magnitude is equal to 16.55. Given that we already know what the magnitude is and that this angle is 25 degrees, we can find the x component, which is this side right here, by just using 16.55 multiplied by sine of 25. And that is equal to 6.99. So I'm just gonna go ahead and round that to 7. This is gonna be -7 because in order to add up to this vector, we need an arrow going up and an arrow going left. And left, in terms of x and y components, is negative. Now, I need to split up every single other force that I have on my problem into x and y components. So let's go ahead and see. So force by gravity is just all on the magnitude is 30 and it's going down. So in terms of x and y components, this basically just means force by gravity is equal to 0 and -30. Force by air is all on the x component and it's all going left. So in terms of x and y components, this is -10 and this part right here is 0. Now TR, we don't know what the magnitude of TR is and we don't know the angle, so we can't figure that out. However, we do know that this part right here has to be equal to 15 because that is what we figure out on part 1 of this quiz. So let's just go ahead and write what we know, and that is that TR is equal to something, which we don't know, and then plus 15 on the y-axis. Now, why am I writing these vectors like this? Well, as we know, this entire swing is balanced, which means that it is not rotating, but also it is not moving in space. Because the swing is not moving in space, that means that if you add up all of the forces acting on your system, the sum of all of the forces has to be equal to 0. So that means that TL plus force by gravity plus force by air plus TR has to be equal to a net force of 0 and 0. As you can see, the y component is already figured out because we have all of the y components, and indeed they add up to 0. So the only thing that we have to figure out at this point is what number should go here in order for this plus this plus this plus this to add up to 0. And as you can see, that number is gonna be a plus 17, so that -7 plus -10 plus 17 is equal to 0. So this is gonna be the x and y components of TR if this angle is 25 degrees. And this basically completes our problem for today. This was definitely a little bit more of a challenging problem, but this was a 7B problem. I took it out of, the archive of the 7B problems. So I really hope that this helped you out. Please leave a like if it did, and I'll see you guys on the next video. It's gonna be angular momentum now. Bye!